All right, let's talk about chi-square distributions. So occasionally we will have a lot of variance inside of our data, and that's not necessarily normal. Okay, so chi-square distributions in particular, the book calls them positively skewed, or not symmetric. I consider them to be their outliers are out here on the right skewed, but you might see in the homework positively skewed. Okay, meaning that your outliers are on the positive side, not on the negative side. Okay, so the idea here is, again, it's not normal, right? Um, Sometimes, though, for instance, if you were in manufacturing and you were, I don't know, making car parts or something like that, you don't want a lot of variation, right? You don't want these weird outliers going on. You want to force this to be more normal. Okay, so that's what happens sometimes is we look at the data and we just go, oh my gosh, this is a real problem. What can I do? Can I kind of force this to look more normal? And I think everybody could probably look at this and say, "Oh, yeah, if I cut off this tail and maybe cut this just a tiny bit, that looks a lot more normal, right? If I just didn't have that and if I just didn't have that." So the idea here is that I can somewhat adjust a data set or adjust a distribution like this and make it be appear to be more normal. Okay, and that's what I said in the last video. I think when I was talking about t distributions was, our real problem is just that we normal stuff is so easy to deal with that when we encounter something like this that isn't normal, we just go, hey, um maybe we could control it a little bit. If we could get rid of all this variation, then maybe we could force it into being more normal. Okay, because more normal is easier for us to work with. All right, so let's go and talk just a little bit about chi-square. So chi-square, and I have no clue why they call it this. It kind of looks to me like a big X, and it literally is squared. Chi-squared, okay? But this is a Greek letter, and it's said Ki, okay? Like pie, but with a K. Okay. So it looks like that, and it looks like a giant X to me, so I usually I will try to put the little tail on it like that, so you'll see it. But when we see this thing, we haven't done anything that looks like a giant X squared, right? So when we see that, we'll go, "Oh, that means chi squared." Okay? So chi squared, what we're gonna do is we're gonna use a method that they call a point estimate. Point estimate. Okay? And the way it works is we find a point of data somewhere in our sample, and we use that to estimate what's going on in the population. So if you'll remember, for a sample, standard deviation is S. Variance, which we haven't dealt a lot with variance, but variance is S squared, right? You can see that if you use your calculator to do certain calculations for you under the stat table. But the variance or the variation that's going on inside of the data points, it's S squared. The standard deviation is just S. Um, the one we're going to deal with the most here is S, but there is a little bit of talk in there about variance. It works exactly the same. It's just dealing with a different variable, just so you know. Okay. So if that's in the sample, what's going on in the population? Standard deviation in the population is sigma, right? Which kind of looks like a 6 on its side. Okay. And if you wanted variance in the population, well, that's just sigma squared, right? Okay. So what we're going to do, the process that they use here, this point estimate is they say, hey, go back to your sample, find your either your standard deviation or your variance. We're going to focus in on standard deviation. Find that data point that you have, you know what that is from your sample, and we'll use that information from the sample to be able to deal with what's going on in our population because we'd like to remember here's what I got. I would like to look at what's right there and make it much, much more normal. Okay, so that's the idea behind this. There is a calculation. So let me just tell you what's going on. If you have a random variable with a somewhat normal distribution, there's always little fudges, there's always little adjustments, right? But we're going to say it's a pretty normal distribution. Then chi-square equals n minus 1 s squared over sigma squared. Okay. For any sample size n greater than 1. Wow. That's really small. Okay. So if your sample size is anything that's greater than 1, basically they're saying you've got a data point here, you've got a data point here. We can normalize that. Okay. You've got a data point there, you've got 2 data points here. We can normalize that. And this is how they go about doing it. 4 data points, 5 data points, it doesn't matter. We can normalize it by using this chi-square. Okay. It's not always appropriate to use chi-square. And again, for instance, the Poisson distribution would be a different setup where we would do different things. But this is kind of the basic definition for your chi-square. Okay, so things to know. Chi-square is always greater than 0. Okay. Chi-square is a family of curves. Why do I say it like that? Because we're going to have degrees of freedom just like we did with the t-distribution. So the idea is the same. And fortunately for us, the calculation is the same. N minus 1 is how I get to my degrees of freedom. So that is not going to change. So fortunately, they stuck with that whenever they were doing all these different types of distributions. So N minus 1 is my degrees of freedom. And what does that tell me? The shape of each of the curves of the family are going to depend on how different it is from the normal curve, right? So, as I get bigger and bigger, it's going to look a little bit more normal, right? So, more degrees of freedom, more data points, and I'll get certainly something bigger n is greater than 1, more data points, and I'll get closer and closer to a normal curve. That's the idea. But these chi-square curves are going to be a family of curves, similar to the ones I had for the t-distribution. Let me see if I can get the picture for the chi-square. Hang on a second. The family. Okay, here's this picture in your book, and you can see, okay, degree of freedom 2 here, this guy, he's way tall on the left, and he looks like that. Degree of freedom 5, he goes up and then comes down and looks like that. Degree of freedom 10, up and looks like that. Degrees of freedom 15, hey, we're getting closer and closer to a normal curve, right? Up and then down. This looks close to a normal curve. And then with degrees of freedom 30, look at this guy. He's pretty flat. He actually looks a little bit more like a t-distribution, right? Okay, so the idea there being that the more degrees of freedom or the more data points I have, that's what that comes down to, right? the more closely resembling a normal curve I am here, right? So it didn't look anything like normal. Looks a little bit like a skewed right, skewed right. Oh, you look normal a little bit. This one definitely looks more normal. So that's what those families are going to be, okay, that we're talking about here. The families of curves, those are all of those I just showed you are all chi-squares, but some of them look a little bit more normal, right? Okay, so that's what they're talking about here. Okay, same thing we had before, both with normal and with the t-distribution. The area under the curve is what? Y'all should be able to tell me this by now. The area under the curve is a 1, Dr. Webster. That's what I hear in my head, right? Okay. Because that corresponds with 100% of my data points, right? 100% is the same as a 1, right? And remember back to your probability. The 1 is very important here. Okay. And then the other thing about chi-square is that it's skewed right. For sure. And like I said, your book calls that a positive skew. Okay. So that's what's going on. These are not symmetric. Um, we know these are not symmetric. And I said this one, but I didn't write it. So let me put it here. The more degrees of freedom, the closer to normal. And we like normal, right? We studied normal. We have a whole set of stuff on normal. So this was point number 5. So we would like for things to be normal if we can. All right. So let's talk about what's going on here. Much like when we did t-distributions, we're going to have to find our critical values. And so they change it just slightly on us. So let me show you what it looks like. Let's say my chi-square looks something like this. Okay. And I want to truncate this thing, let's say like that. Okay. Instead of t sub c, which we had whenever we did t distributions, right? They call these chi-squared left and chi-squared right. Okay. There's still going to be like fences, right? I'm still going to kind of have my X bar going on in here, the middle of my curve, so to speak. We know it's not the middle because this end's going like this, pulling down. But my two fences, I'm going to have a left-hand side, that's the L, left-hand chi-squared, and I'm going to have a right-hand chi-square. So let's think about it, okay? Again, if I'm cutting this graph off, then the idea is that my confidence level, whatever confidence level I'm at, I'm going to go with 95% for right now. My confidence level is right there in the middle. Okay. And we can see because it was skewed, I've got some extra data points over here maybe than what I had there. Okay. But the idea here is very similar. Okay. Um, we're going to have down here 1 minus c over 2. It becomes a little bit unusual up here. This is also 1 minus c over 2, but what happens is because we're on the positive side, it's like a negative and a negative. This actually becomes plus, okay? So plus the whatever is left over. I'm sorry, that's not right. 1 minus c, I'm going to have this is where it's going to get kind of confusing. Let me show you what it looks like. 1 minus c over 2. Let's start with that. 1 minus c is 95%, right? C is 95%. So this is 5% divided by 2. This is 2.5%, right? Is what we're looking at here. 2.5% on both of them. But in order for me to find the number over here, what happens is I'm looking at 1 minus c over 2. So it ends up being, oh, that's not quite right either. I'm sorry. Let me just say it's 2.5%. I'll come back to this to give you a better explanation of it. Okay. So the 2.5% guy here, basically it ends up being 1 plus the C over 2. So it looks a little bit different whenever I do that. And it's because this is not symmetric anymore, right? Um, let me see what I can find. Give me just a. All right, I'm sorry. I've got it. I don't know why I didn't write this down before. So, when we're looking at this particular guy, what's going to happen is the number that we're going to find in our table is going to give me the area to the right of these numbers. Okay. So, the area to the right of these numbers, okay, if I'm just right here, that's just the 1 minus C over 2. No problem, right? The area to the right. But if I'm doing all of this, okay, I've got this 1 minus C over 2 for sure. But if I'm getting all of the area to the right, so the difference is they're not telling me the 2.5% here. They're telling me the C, all of this stuff, the 95%, plus the 1 minus C over 2. That's what I was trying to get at, okay? So, the numbers that I'm gonna find, it's important to know. So, when I find chi-squared left, this gives me the area to the right when I look in that table. The area to the right of chi-squared left, okay? And when I find chi-squared right, it's also the area to the right. But in that case, it's just chi-squared right. Okay. So the difference being that the area to the right of this number on the right is smaller than the area to the right of this number on the left. Does that make sense? I hope so. Oh, right. Okay. So that's why I should have written down that calculation. I'm sorry. This guy. What's going on? Okay, so let's look at an example and we'll see what happens. Okay, so that we can work on it. Okay, the table's going to show me all the different degrees of freedom as well. So once I figure out the degrees of freedom, then we'll work on that. Okay, so here's my example. Find the critical values. And pretty soon I'm just going to call those CVs because I'm going to be the lazy mathematician for chi-square right and chi-squared left for a 95% confidence interval. Confidence level, I should say. It's not quite the same as confidence intervals we've been doing with the normals. When your sample size equals 18. All right. So before I run off and do anything, I've want to do the first thing that we talked about with t distributions as well, which is find my degrees of freedom. N minus 1. So in this case, it's the number of samples, 18 minus 1 or 17. So my degrees of freedom is 17 that I'm going to be looking at. Okay. It's also important for me to notice the 95% guy here, right? Okay. So let's figure out what the two different areas are going to be here. Okay. So I've got um, the area to the right of chi-squared right. The area to the right of chi-squared on the right. Let me redraw this picture because the one I had up there was terrible. All right. Here we go. Something like this. And what we said was we're going to have chi-square right, and we're going to have chi-squared left. Okay, so the area to the right here is just this little bit here. And I can still say the whole area is 1 minus the 95%, 0.95. That'll give me the 5% in this case, divide by 2. Okay, so This part right here is not terrible for me because I can do that okay, right? So this is 5%, 0.05 over 2. This is 0.025 or the 2.5% we were used to. Okay, that's not bad. Okay, that's the proportion I'm going to get over here. But when I come to do this area from the chi-squared left all the way over to the right, I have to add in this 95%, right? Does that make sense? Okay. So when I add in that 95%, it's going to be 95 plus this 2.5%. Well, what's that? 95 plus the 2.5% is 97.5% or 0.975, right? Okay. Is that all right? Okay. So those are the two numbers I'm looking for. I'm looking for the area that's only 2.5%, and I'm looking for the area that's only 97 or that is total of 97.5%. And the reason why this one's a little bit different is because the chart for this is a little bit different. Okay. The table that they give me. It's not because it so when I did T distributions, it was just find the positive and make it negative because that was a zero right in the middle, right? This is not 0 right in the middle. So instead, they don't give me a positive and a negative like that. They're like, find this little tail and then find the total of that. Okay, so let's look at the chart and we'll see. So, as a reminder, we're looking at 95%, 17 degrees of freedom, and let's start with the 2.5%, which is 0.025. Okay, here we are. So, first off, um, 0.025, and I think I said 17 degrees of freedom. 30.191. Does everybody see it? 30.191 is the number that is my chi-squared on the right. 30.1. I'm sorry, hang on. I just want to make sure I put it in the right spot. Yeah, 30.195. 191. It's my chi-squared right? Because that was the 0.25, 0.025. Okay. So, what about this guy on the left? He's a 0.975, okay, 97 and a half. And he's also 17 degrees of freedom. So let's find that guy. He's way over here, 97.5 and 17 degrees of freedom. There we are. That is says 7.564. 7.564. Okay. All right. I like it. It helps that that matches my notes too. Okay. Yay, we got it. Okay, so what are we looking at here? Yes, this is not a necessarily a normal distribution, okay? But if we want to make it look like a normal distribution and pick 95% of the data points, what we need to do is look at the data points between here and here. 7.564 and 30.191. So if you remember confidence intervals, what you're looking at here is you're saying that 95% of your data points can be found in that region, okay, in that area of the graph. Okay, yay. All right, let's see if we can do another example. We like lots of examples whenever we can get them. I would like to do a similar thing to what we did before, which is I'm going to give you your example. I'm going to ask you to write it down. Find chi-squared left and chi-squared right for a 90% confidence level. If your sample size is 30. Okay. So again, I would like for you to pause it for just a second, start with degrees of freedom, all of that kind of stuff, and I will put up the table for you to look at. Make sure you have all that written down, and then push pause. Okay. Here is the table. So hopefully you did your degrees of freedom. 30 minus 1, 29. That's what I'm looking for degrees of freedom, right? Ooh, excuse me. And you're looking at 90% now. So we have to do the little adjustment. We can't just go jumping right in. So hopefully it's because it's not necessarily it's not a normal curve here, right? So we're looking for this number and this number. And we want 90% in here. C was 90. Okay. So if you did your little math here, remember this piece right here is 1 minus 90 over 2, which is 10 over 2, which is 0. I'm sorry, 0.05 because it's 5%, right? 5% is 0.05. Okay, but that tells me what's to the right of that value, but this guy right here, whenever I find him, remember it's the 90 plus that, right? Okay, so 90% plus the 5%, 95, right? I'm sorry, hang on just a second, let me get it. It should be the 95 divided by 2. That's not quite right. I need a 195, right? Okay, going back to it, I'm sorry. On the last example, I kind of cheated on it. 97.5. It should have been the 1 plus the 95 is 195 divided by 2 gives you the point 1 and 0.975 or the 97.5. So what I'm missing here is I need to add these together. So I've got the 1.1 plus the 0.9, 1.9 over 2 is 0.95. Okay, so the left guy, chi-squared left, is going to be 0.95. I'm going to look for him on the chart. And the chi-squared right guy is going to be the 0.05 guy. And I'm going to look for him on the chart with 29 degrees of freedom. Let me find the chart again. Sorry, it got kind of sideways on my stuff. Okay. So for the 0.95 and 29 degrees of freedom, here we are. Yes, this is correct. Oh, there we go. 0.95, 29 degrees of freedom, 17.708. That's what's going on the left-hand side. 17.708. That's my left-hand fence, right? Okay. And on the right-hand side with 29 degrees of freedom off this 0.05. Oh, goodness. Here he is. Good. That is also the number I have in my notes. So 42.557 is my right-hand fence. All right. So let's interpret this and see what the heck's going on here. So what we're saying is 90% of the data points in a chi-squared distribution with 30 samples, 30 data points, fall between 17.708 and 42.557. That's what we're telling you. All right. And we know that they are not normal because again, my picture is definitely not normal there, right? Kind of looks like some of my normal graphs might look, but but we're gonna say it's not normal because it's got that tail. So here's the upshot of this. Because chi-squared isn't symmetrical, that's the whole point of this. Because it's not symmetrical, we can't do s plus or minus the error. Okay, this is what we did for normal, right? Okay, this is what we might do. Instead, we have to use a calculation, basically. Calculations to find the endpoints. For my confidence interval. Okay. So there are a couple of calculations for this. You're not going to have to do this for sure. I just want to show you how it works in one of the word problems. But again, you're not going to have to do this on a test. It's just so that you understand what's going on. So confidence interval for, and we're going to do sigma, because we're going to deal with standard deviation. What we have is the square root of n minus 1 s squared over chi-squared r, the r guy, okay, is less than the sigma guy, is less than n minus 1 s squared over chi-squared L. Okay, and the reason why they switch these on me, the left guy goes on the right and the right goes on the left, is because if you've noticed, all of my right-hand guys were bigger, right? The number value was bigger because the left was on the left-hand side. So on my number line, the left is bigger or left is smaller. But whenever I divide here, dividing by a bigger number, what happens? Like if you divide by 2, you take a half of something, you've got a pretty good chunk. But if you divide that something by 4, you take a fourth of something, your chunks are smaller, right? So what's happening here is they're using the idea of the bigger the denominator, the smaller the thing. And so they're putting this R guy, the right-hand endpoint, on the bottom here because whenever I divide, I'm going to get a smaller number than when I divide with a smaller number on the bottom. Okay. And what's this square root stuff? That's because s squared is the variance, right? And we're talking about sigma. If I was going with s squared with variance, then that would be sigma squared for the population. That's a different set of formulas. And basically, we don't use the square root, right? So it's smaller than the variance. What happens whenever I'm dealing with sigma? Okay. Um. Okay. I've got a note here that says the probability confidence interval contains um containing sigma is C, assuming the process is repeated a large number of times. So that just they're trying to bring in the law of large numbers there. You got to do this a lot of times before you can say for sure it's happening. Okay, here is the example. Example. You randomly select and weigh. Randomly select and weigh 30 samples of allergy medicine. Okay. Now, what do we think about that? If I got 30 different samples of the same allergy medicine, hopefully they all weigh the same, right? So I don't have one that weighs, whatever huge amounts of milligrams and the other one weighs a small amount. I want these to be as uniform as possible, right? So that's the idea here for why we're going to use chi-square. Okay. This you find that the standard deviation equals 1.2 milligrams. Now, this is on your sample, right? So this is S equals 1.2 milligrams. Okay. Assuming that the weights are normally distributed, okay, that's one of the rules for the chi-square is that my whatever my data point that I'm looking at, in this case it's the weight, that had to be normal, right? Okay, so and that's probably the case whenever I'm dealing with just random samples. So, assuming that they are normally distributed, construct a 99% confidence interval for the standard deviation of the population. Okay, so what they're saying is we are only weighing 30 samples, but we'd like to be able to say something about the entire population, right? That's the idea. We'd like to infer. Okay, let's do our little math thing that we did a minute ago. The areas to the right of chi-squared are on the right-hand side is that's 1 minus c over 2. That's 1 minus 0.99 because they asked for, where'd it go? 99% over 2. That is point 0.1 over 2, or I'm sorry, 0.01 over 2, or 0.005. Okay. We'll come up with a number for that in a minute, but that's the area to the right. Okay. How about the areas to the right of chi-squared left guy? Remember, we changed that to 1 plus c over 2. So that's 1.99 over 2. And if I divide that out, that's 0.995. So punch that on your calculator. Make sure you're getting that number. Remember on the left, that's the huger because we're going the entire 99% plus the 0.005%. So it's a lot larger area on the right for that left-hand guy. Okay. And the last thing we need to be able to do this is we need to do what? The degrees of freedom, right? Which we know is n minus 1. There are 30 samples. 30 minus 1, 29 degrees of freedom. Okay. If we have all of that, then that will give us our information we need for the table, the chi-squared table. So I need chi-squared left and